I warmly welcome you to this afternoon's session on Global Assessment Report. My name is Kamal Kishore. I'm from UNDP. I've been asked to help facilitate this session. This is going to be a very interesting session. We are going to discuss Global Assessment Report on Disaster Risk. Since 2007, this whole process began. In 2007, a review of various global reports was presented at the global platform. 2009, the first global assessment report came out. 2011, second assessment report came out. 2009 report focused on poverty and risk in a changing climate. 2011 moved the focus to addressing issues of governance. This has truly been a path-breaking effort in more than one ways. Substantively, it has not only presented in a coherent fashion a model of global risk, which not just looks at the aggregates, but also what's happening at the local level, and identified the key drivers of risk, try to understand what goes into the buildup of risk and how we could do better in reducing and managing that risk. Equally importantly, the report has become, the UN's at least, a flag bearer in the sense of advocacy efforts. The 2011 report alone, the chapters of the report have been downloaded 300,000 times. So in less than a year. So which means at least 100,000 people have it on their computers, and we're not talking about printed stuff and references made in various advocacy efforts. One of the areas of the report which requires further work is modeling drought. And you will see that this afternoon session will begin to address the problem of drought. But before we do that, I would like to invite Andrew Mascari. He's the coordinator of this entire effort since the very beginning. He needs no introduction. He has been a global leader in the area of disaster risk reduction from the times of the International Decade of National Disaster Reduction, and even before that. Some of the first interesting literature on community-based disaster risk management, local level disaster risk management was authored by him. He is a leader in this, a thought leader in this area in many ways. So without further ado, I would now invite Andrew to give the introductory presentation on the assessment report.
Okay, thank you very much, Kamal. How do I actually get my presentation up? Do I just click on something here? This one?
This one?
Yeah.
I haven't got it. This is the one. I don't have this one. No, the one that you gave me. My apologies.
Very good. Thank you very much. For those of you who are in the Ignite session yesterday, there won't be many surprises because it's exactly the same as what I'm going to present now, except that this time I'll actually have the opportunity to talk about the slides instead of just flicking through them quickly. But basically, what we're going to do, we'll look at, in a sense, a selection of some of the information that's come out of the last two reports, 09 and 011, and also some of the perspectives which will feed into the next one in 2013. As Kamal said, this is a biennial report every 2 years. It's a UN report launched by the Secretary General. So it's not just a UN ISDR report, it's a report on behalf of the whole system. And we really try and make this a global effort in which, you know, typically 50, 60, 70 partner organizations feed into. So let's see if I can go. One of the first things we've done in the report, and this is really from our 2009 report, We have a global risk model, which is an effort of a lot of different scientific and technical organizations working together, where we've tried to really map patterns of risk, where different kinds of risk, mortality risk and economic loss risk, are concentrated in the globe. In absolute numbers, and these graphs look at mortality risk for multiple hazards. Unsurprisingly, risk is actually very heavily concentrated in just a few countries. And in absolute numbers, most of those are the very large countries in Asia, which simply because of the size of their exposed populations, China, India, Bangladesh, Indonesia, are the countries which, do concentrate most mortality risk. But when you look at risk in relative terms, in terms of just the killed per million per inhabitant, we get a very, very different selection of countries out there. And this really includes many small island developing states, and also some of the small countries. Africa is not well represented in these figures for one simple reason, that in 2009 and 2011, and we'll talk about that a little bit later on, we weren't able to incorporate drought risk at all into these calculations. So this is one of the reasons at the moment why African countries do not figure very highly in these statistics. When we think about disasters, we generally think about the large-scale catastrophes which reach the headlines, the disasters in Japan, Thailand, Pakistan we've had in the last year or two. But for most local communities anywhere in the world, disasters are essentially local. And a significant part of the loss is actually associated with very, very small scale, flash floods, landslides, localized storms, localized droughts, etc. And with the report, we're gradually trying to make also an effort to map and to understand this other kind of risk. We call this extensive risk to really differentiate it from the major catastrophes, which we call intensive risk. These two maps are of Sri Lanka in South Asia, and we've just shown on the right-hand map, number of disaster reports of intensive risk. So these are the very catastrophic events since 1970, mainly just around the coast, mainly associated with the 2004 tsunami. But if you look at the extensive risks, which is all these small-scale events, what you can see is affecting every single municipal area in the country, and with many municipalities actually reporting more than 100 disaster events over, less than 30 years. So this gives you less than 40 years, sorry. So it starts to give you an idea of, two different segments or layers of risk which we need to understand quite well. In terms of hazards, we've got a reasonably good, I think, global understanding now of hazard distributions, and we can actually understand drought as a hazard. Understanding it as a risk is a lot more complicated. So, globally, we have good models now of the distribution of floods, tropical cyclones, earthquakes, and drought. We know that, climate change is going to certainly affect the distribution of the hydrometeorological hazards in the future. But as anyone who's read the recent IPCC SREX report will know, moving from general statements in terms of how this may change into the future, in terms of actually understanding the local implications of this for specific hazards in specific places, is still a complicated challenge. But what we do know is about the exposure part of the risk equation. I think most of us know the risk is made up of hazard, intensity, exposure, and vulnerability. And most of the increase in risk, which we've been seeing in the last 20 or 30 years, is actually driven by increases in exposure. And this is particularly in the case of countries and regions which have had very rapid economic growth. This is a map of population exposed to tropical cyclones in China, but we could produce maps of many areas of a country like this. So this isn't particularly difficult to understand. If your GDP is growing by 10% a year, and most of your economic assets are located in areas exposed to cyclones or floods or other hazards, then your exposure to these hazards is also going to be growing by 10% a year. And this is what's happening and has been happening in many countries of the world. It's a real accumulation of risk. On the vulnerability side, in the first report, in the 2009 report, we did a lot of statistical regression analysis between the risk parameters and different sets of social and economic vulnerability parameters to try and really understand what was explaining and what was driving the risk. And clearly one of the first and most important drivers of risk is poverty. Put simply, countries with a low GDP per capita are much more likely to have very, very high levels of mortality compared to countries having a very high GDP per capita, everything else being equal. So these two graphs actually compare Philippines and Japan. Both countries have roughly similar numbers of people on average exposed every year to tropical cyclones. But when we did the calculation, we saw that, Philippines would typically have 17 times more deaths than Japan for the same number of people exposed to the same kind of cyclones. And when you actually compare different groups of countries, the differences can be even more marked. If you compared OECD countries to the LDCs, the least developed countries, again, for cyclone risk, the difference is something like 200 to 1. So this is telling us, that this distribution of risk globally is extremely skewed, and it's extremely skewed, against the poorest countries. So poverty really does play a huge role in actually constructing and determining these risk patterns. A second factor which we identified was related to, urban growth, but also to levels of governance. There are actually indexes out there now of governance quality, which one can measure vis-a-vis risks. These 5 graphs are from a city in Colombia, in South America, Cali. It's a city which has an excellent citywide disaster database right down to the local level, which has been keeping since the 1950s, which is actually a major achievement in itself. But the graphs basically show just at a very, very local micro level the occurrence of floods. Yeah? And what you can see is basically from the 50s, the 60s, the 70s, the 80s, and the 90s, the occurrence of floods almost moving out in concentric circles from a core in the center. And what you're basically seeing here is just the expansion of the city, particularly the expansion of low-income squatter settlements in the city. So if you put together low-income squatter settlements, mainly being built in low-lying flood-prone areas and with no drainage infrastructure, that is like saying equals floods. So this is a pattern that's not just unique to Cali, it's common to many cities in the world, and in fact common to many, many African cities. So really we also have to understand, these deficiencies in the way we're planning and managing urban development as again being one of these major drivers of risk patterns. And the third one, which the 2009 report identified, was really, declining ecosystem services. So these are the roles played by forests, mangroves, wetlands, and other ecosystem services in actually managing and mitigating, different kinds of hazards, floods, storm surges, drought, and so on and so forth. These maps, again, just compare in another South American country, Peru, landslide occurrence before, instance, the mid-80s. The right-hand map, you can see a large kind of concentration of landslides in an area which had never, ever occurred before, linked basically to deforestation after the construction of a major road into the forest. But these risk drivers actually play out in 2 very, very different ways, depending on whether we're looking at mortality or whether we're looking at economic loss risk. In the case of mortality, the exposure, almost in any region in the world we look at, has gone up. We have more and more people living in hazard-prone areas. But in general, the vulnerability part has been going down because countries have been getting better in terms of disaster response, disaster preparedness, early warning, systems of different kinds. So in general, the mortality risk is going down. And according to our calculations, from the risk model, in some areas it's even gone down. This is East Asia and the Pacific for cyclones, has gone down something like 50% since 1980. But in terms of economic loss risk, the same is not happening. We've still got the exposure going up, like more and more exposed assets in hazard-prone areas. But countries are having much more difficulty in addressing the vulnerability factors, which are much more related to land use planning, environmental management, social protection, environmental management, and so on and so forth. So if you have exposure going up and vulnerability either steady or not going down, then the risk is also going up. And in some regions, this is actually the OECD, these are the rich countries. We just compared this almost as a teaser with GDP per capita and found that the risk of economic loss was going up faster than GDP per capita, which formally means that the risk of losing wealth in disasters is rising faster than the wealth is actually being created. Losses, therefore, are increasing, losses of physical infrastructure. It's very difficult to measure this if you just look at the large-scale events that in any one country maybe only happen every 5 or 10 or 15 years. But if you look at the losses from the small-scale events, so these are all these extensive risk events that are happening every year, it is possible to do some time series and really look at changes over this period of 20 to 30 years. These are some figures from Indonesia. We have, I think, in the audience somewhere, Ridwan from Indonesia, who actually put this database together from us. Where's Ridwan? He's at the back. Again, typical pattern of extensive risk, losses all over an entire country. But interestingly, when we looked at, for example, at schools and health facilities affected across the different countries where we have data, we saw, typically a kind of a 10-fold increase over 1980. Some of that may be due to better disaster reporting, better information. It's difficult to check for that, but we know it's there. Some of it may be due to, climate change as well. Again, very, very difficult to prove. But let's say the strength of the curves indicate the losses really, really are going up and going up very significantly. And these, I think, are gradually turning into serious issues, serious impacts for governments. When we've had dialogues with finance ministries in the last year, it's almost a recurrent echo from all these meetings that the value of these losses, the losses for which governments have responsibility, fiscal responsibility, are now getting so big that they are actually bringing the subject into the finance and planning ministries. The ministries are actually saying, well, this is now an issue that's hurting us, and this is an issue where we now need to develop strategies either to reduce the risks or to manage the risks or to transfer the risks one way or another. Interestingly, these impacts don't affect all countries equally. And we've done now, again, this is from the 2009 report, but we worked on both 2009 and 2011. We've worked on modeling how, some of these impacts affect different kinds of economies. And in these 4 graphs, we've really taken 2 extremes. We've taken 2 of the largest countries in the world, the USA and India, and we've taken 2 of the smallest countries in the world, which is Santa Lucia and Samoa, 2 small island developing states. And we've just compared, it's a simulation of net capital formation over time, and then what would have happened if you then take into account the disaster losses on this capital formation. And basically as I said, these are really 2 extremes, so it's nice as an illustrative example. Most countries fall between these 2 extremes. But basically, in the case of, very large economies, very diversified economies, economies which are well linked into the global economy, well on competitiveness, etc. Generally, the disaster losses really represent only a kind of a blip, a slight blip in terms of total capital formation. But in very, very small economies, particularly those where the economy is concentrated in just one sector, so I mean, typically say a small island where 90% of the economy is maybe in tourism or is in one agricultural sector, these losses really can be devastating for the whole economy. And these are really the cases where you do talk about decades of development being wiped out and enormous difficulties in recovery. Ultimately, I can't remember who it was 20 or 30 years ago coined the phrase that disasters are unresolved problems of development. I'd like to say it was me, but it wasn't, because I remember reading this like 20 or 30 years ago. And this is still really true. If you look at a range of development indicators, and this can be anything from the Human Development Index to GDP or competitiveness or whatever, and then actually cluster the countries to see the patterns. Apart from the OECD countries, most of the developing countries fall into two quite distinct groups. One group which has been, since the early 80s really converging steadily on the OECD. So you could call these converging developing countries. And another group which has either not been converging or actually diverging, both from the OECD and also diverging from the other developing countries. And this is actually important because we often talk about developing countries as though this is a homogeneous group, and it is not. When we compared this again with the risk model statistics, what you can basically find is the converging countries are the ones where we have this really rapid growth in economic loss risk. I mean, these are successful economies where we have more and more exposed economic assets and the economic losses are still going up. But the diverging developing countries, so this is, the Haitis, the Somalias, the Chads of this world. These are the countries where we don't have the same pattern. These are the countries really where the mortality risk is still extremely high and still going up. And this is borne out. I mean, when you see disasters like the Haiti disaster of 2 years ago. This graph shows population and economic assets exposed to tsunamis. Again, this is from data from the 2009 report. It's not really surprising. Japan is second in terms of average population exposed per year to tsunamis, and first by an enormous margin in terms of economic assets exposed. This we know. But I think what we don't know is then really how to model the downstream impacts of very, very extreme, very unusual, catastrophic events. And what we saw, I think, in Japan last year was a mixture of between what we call synchronic failures, where different systems break down at once, and sequential crisis, where one kind of disaster creates another. As our societies become, increasingly urbanized and increasingly dependent on telecommunications, internet, electricity, etc., clearly, I think this gives us a little bit of a taste of what the future of risk is going to look like, and probably the inadequacy of much of the modeling work we're currently doing, which still tends to look at natural hazard risk in a silo. And I think we're still not very clear in terms of how we can actually then model the more societal risks which come out of that. Every 2 years, we ask governments to self-assess their progress against the Hyogo Framework of Action, which is the international framework we have for reducing disaster risk. The last time we did this, between 2009 and 2011, 130 governments actually did this assessment. So we have a lot of data. It's actually, I think, the biggest global archive on actually what governments are actually doing in risk reduction. But without going into maybe too many details of this, what this graph tells us, this is average progress across the whole world against the 5 Hyogo Framework of Action priority areas. What governments tell us really just corroborates what the risk model tells us. Countries are doing very well in Area 1 and in Area 5, which is basically creating institutional and legislative frameworks to do disaster preparedness and response. Yeah? This is where countries are having success. So we have better response systems, better preparedness systems, and to some extent, better early warning. And this is why, you know, with exceptions, we still have Haiti's happening, we still have Myanmar's happening. In general, the trend in terms of mortality risk is going down. But where countries tell us they are really challenged is particularly in Area 4. That's happened in both these exercises we've done, which is actually getting disaster risk considerations factored into the different kinds of development planning, so into environmental management, social planning, urban planning, infrastructure development, and so on and so forth. And this is, it's not me telling you that this is where the problem is, this is governments telling us that they either can't do this or they're very challenged to do this. And this is really where we're not making progress, and this is really where we can see, as I said, the corroboration of why the economic loss risk is going up so fast. In this Hyogo Area 4 of underlying risk factors, we then asked countries a lot more detailed questions, and we got answers from them on these more detailed questions. I just ask you to focus maybe on the right-hand bar chart, which is where we asked countries whether they were able to use urban and land use planning to reduce risk. And I think anyone who knows about disaster risk reduction, you'll understand that urban and land use planning should be one of the primordial tools that we can use. If we can't actually influence where things are being built, we're not going to really be able to influence whether risk goes up or down. But I mean, in this case, again, something like 70% of the high-income countries said, yeah, we use urban and land use planning as a DRR tool. Great. So that means they're not building so much in floodplains or along fault lines or on very exposed coastal areas. But if you go down to the low-income countries, it was only, I think, around 14% that said they were either could or able to use planning as a tool, which basically means more than 85% couldn't. So again, this is, this explains to us what's really happening on the ground and why we're having this difficulty in getting this traction in addressing risk. So some of the issues we've been pointing to, and this is really now from the 2011 report, one is clearly the need to systematically account for our losses. And again, this is something we're still not doing very well. From global databases, we can get a part of a picture. From the CRED database, I think we can get a reasonably good idea of mortality, but they don't look at really physical losses. From the big insurance databases like NatCat and Sigma, we can get a great idea of losses in well-developed insurance markets, but probably not very much about what's happening in remote areas in developing countries. So one of the key things I think we have to do is to really get countries and governments committed to systematically accounting for their losses, because if we really don't know what we're losing, it's very, very difficult then to justify asking anyone for more investment. We also then need to really look at what we might be losing in the future, and this is really where probabilistic risk assessment comes in, which is being discussed in many other sessions in this Understanding Risk conference. Because clearly, if we only have 40 or 50 years of loss data, that can give us a reasonably good idea empirically of what we may be losing in return periods of less than 50 years. It gives us a very good idea of, if you like, the extensive layer or segment of risk. But we really do need the typical catastrophic probabilistic risk assessment to give us an idea of the losses we might incur, the intensive losses from 1 in 100, 1 in 500, and 1 in 1,000 year events. So combining this, I think, we need to start developing risk footprints for every country, and we can use these risk footprints then to really start having dialogues with the government in terms of what they should be or could be investing both in reducing part of these risks and in insuring or transferring through different mechanisms other parts of this risk. And we can use these curves to then really identify different kinds of risk strata. This again is a graph from our own risk model. If we say that risk again is made up of hazard intensity, exposure, and vulnerability, clearly there's nothing we can really do about the hazard intensity. I mean, if we're going to be hit by a Category 5 cyclone, I as a government might pass a law saying the cyclone should turn to Category 1, but the cyclone won't. I mean, we can't legislate against hazard intensity. And we can't do very much about exposure as well. You know, I might, again, decide that I really should relocate Cape Town somewhere else, but Cape Town's here. Most cities are going to stay where they are as well. So really the only thing we can do is reduce vulnerability. But what this graph tells us is maybe not too easy to understand, but we're looking at 4 different categories of tropical cyclones. Cyclones are measured from Category 5, which are the most extreme, to Category 1, which are the, let's say, relatively low-level ones. In the case of the Category 1 cyclone, something like 90% of the risk is actually explained by the vulnerability and only 10% by the exposure. So if 90% is explained by the vulnerability, actually reducing the vulnerability gives us a huge opportunity to reduce the risk. Yeah? By the time you get to the Category 4 cyclones, the vulnerability is only explaining something like 40% of the risk. 60% is explained just by being there. So that means that even if we could really reduce our exposure, our vulnerability to 0, we're still left with 60% of the risk. And this, I think, points to, again, to this importance of layering risk. Governments can and should be investing in reducing the risks where if we can reduce our vulnerability, we can get rid of a lot of the risks. These are the ones on the more extensive side of the spectrum. But on the more intensive side of the spectrum, where however much we invest in vulnerability reduction, we're still going to be left with a lot of risk. This is really where we have to be looking at, the different groups of risk transfer instruments, insurance, reinsurance, cat bonds, contingency financing, and so on and so forth. We also looked at, some of the costs and benefits of different strategies for risk reduction. And what came out of these modeling exercises, again, it's fairly intuitive. I don't think it's anything very surprising, but we get much more bang for our buck if we can actually use, planning and design to avoid the risk happening in the first place. So, I mean, if we can actually, the additional cost it would cost us to make sure that things were built in safer locations and to higher standards, the benefits would be around 4 times greater than the avoided costs of rehabilitation, reconstruction, etc., if we didn't do it. But if we actually had to invest in relocating, rebuilding, and retrofitting stuff which is already in the wrong place and already not built to good standards, the cost benefits are often fairly marginal. So it's really telling us, I think, of the importance of really proactive, prospective risk management. And then to finalize, our greatest challenge of all is really how we organize ourselves to do this. And again, if any of you actually would like to take the time to read these 130 reports from governments which come in on the HFA Monitor, and I would encourage you to actually do so, because this is really where you learn, I think, what's happening out there. 3 issues, I think, really came up. One at the central government level, the importance that this subject, the theme in any country is anchored in a part of government which can both ensure political authority and coherence across the sectors. If disaster risk management is anchored in a part of government which doesn't have any influence over the education sector, the health sector, the transport sector, basically these sectors are going to continue doing business as usual, and we're going to get nowhere. So we need to make sure that in the central government, it's really anchored in somewhere which has both the political authority and can bring coherence across the different government sectors. In terms of local government, decentralization has become almost a kind of a mantra. A lot of what we know needs to happen, has to happen locally. So in principle, decentralization is good. But the experience from many countries in all continents, and I think South Africa was actually one of the countries that talked about this a lot in their national report, when the responsibilities get decentralized, but there isn't an adequate decentralization of the resources and the technical capacities to actually fulfill those responsibilities, it's actually possible to make the problem worse. So we do need to look at how we can actually decentralize step by step in a way that we actually bringing the technical capacities and the resources down at the same time as we're bringing down the legal responsibilities and mandates for DRR. Just one anecdote. I remember a post-disaster recovery program when I was in UNDP in about 2001. We were trying to develop after an earthquake in a rural area. And the team who put together the assessment came up with, the usual wonderful recommendations of building back better and using seismic-resistant technology and this and that and the other. But we then discovered that the 21 most affected municipalities didn't have one single civil engineer among the 21 municipalities. So that's when, in a sense, a lot of what we talk about hits reality on the ground. And last but not least, I think a lot of countries tell us they're still really challenged to work out of government. I mean, to actually have creative partnerships with civil society and civil society organizations in a way that can actually ensure, ownership and sustainability of whatever we do on the ground. And again, anyone who's seen drainage infrastructure built in informal settlements, often, expensive interventions, expensive investments from the government side, but 5 years later just don't work because they're blocked with garbage or have just fallen into complete disrepair because there's no ownership on the community side. This is a real problem and a real issue. So I will stop there. Thank you very much. All this information is available online, and thanks to Julio, who's the second one there, even if you don't have a good internet connection, you now don't need to download any of this stuff. It can actually just all be consulted online, which makes it, I think, easier for those who don't have the facilities to start fast downloading huge archives. So thank you for your attention.
Thank you, Andrew. In the interest of time, we will go through all the 4 presentations and then take questions. May I now invite Professor Wadid Arian. He is Director of Land and Water Use Division at ACSAD, which is Arab Center for the Study of Arid Zones and Drylands. He is one of the lead authors of the IPCC SREX report. He wrote the case study on drought. He has led the development of World Bank's climate change adaptation strategy for the Arab states region. He is on the advisory panel of the GAR, the Global Assessment Report for 2013. Professor Arian.
Mr. Chairman, thank you very much. Good afternoon, everybody. So this is the map I'm going to show you all the time now. I have 130 slides. And I have a challenge to do it in a very short time. So, but this is very important, the key message coming from the SREX report. And if you read the first line with medium confidence that drought will intensify in the 21st century, let me tell you that it is medium because the knowledge and the information was limited. So I can give it high level of confidence, but it's only because of the limitation of information available. It is medium. So those are the regions which will going to suffer, but Mediterranean and parts of Africa, especially South Africa, and will be affected by drought. But what's the definition of drought? Drought is very complex phenomena, and finally we have now IPCC and agreed that in the new definition, just published in April 2012, they said that this is exactly the definition of drought. Drought here is a period where is abnormally dry weather, long enough to cause a series of hydrological imbalance. If it is precipitation deficit, so we call it meteorological drought. If it is soil moisture less than usual to support vegetation growth, so we call it moisture drought or agricultural drought. This is what we're going to talk much about now. And if it is not enough to support the runoff of water, rivers, so we call it hydrological drought. And here we can see that evapotranspiration is taking place now in the definition. So all the time we speak about SBI. When we speak about drought, this is not anymore. Now we are going to talk about different indexes, including evapotranspiration in it. And what is new here is that we are talking about mega drought. This is a decade of drought. So we are expecting to have, in many places, decade of drought. So this is what we call mega drought. And as just has been explained now by Andrew, we have the hazard. So we would like to understand, first of all, what is the shape of the hazard and what is exposure to it, and then come to vulnerability and risk analysis. So this is the way we are going to deal with the subject, and that's why we draw this diagram. Those are the steps we are going to follow. We are going to talk about how we can reach to drought hazard and how to calibrate it with SBI. And at the same time, we will see how the land cover or land use is exposure to drought. And we will see also how the river basins are exposure to drought, keeping in mind that we have more than 236 river basins and lakes around the world, transboundary. And we'll see the vulnerability in the loss of land use and loss of crops, and then we will do some analysis, statistical, to see exactly how this affects the economy and social. So if we talk about drought, we have to keep in mind immediately that there is intensity here, but also there is variability, because in many places in the world, the precipitation is not coming similar way, similar shape, similar months. There is a variability in amount and in distribution. So it's very important to include variability. And also it's very important to see the frequency of drought and consecutive, the duration where you have drought expanding for a few years. If we have all these four, intensity, variability, frequency, and consecutive, then we can talk about drought hazard. So we'll try to see if you study a country like Africa, where you have the rainfall distribution and rainfed agriculture distributed in different systems. Then the first step you have to do is to identify the agriculture seasons, rainfed seasons. And this is what we have done by studying NDVI, and we came to this map, number of months where we have different months for agriculture seasons, and we came with this map where we had identified the seasons expanding and which period for each area in Africa. And this is our final map for rainfed seasons. So we are going to use the satellite images. So we have MODIS and we have indexes like vegetation condition index, temperature condition index to calculate VHI, vegetation healthy index. And vegetation healthy index is going to be used as an indicator for intensity, and then we will use it also to estimate the rest of the other parts of drought. So we need photos for different agriculture seasons. For instance, if you have winter areas, like in the northern of Africa, Mediterranean, so we have around 8 to 9 months, and for 11 years, we estimate for all VCI, TCI, and then we calculate VHI. So from there we can come to calculate intensity, variability, frequency, and consecutive. And if we do so, we can use the 4 maps, and I'm giving just an example here for Syria, to see that if you have the intensity map, and you add to it the variability map, and you add to it frequency and consecutive, you can come with the map of intensity. And this is the intensity map of all the study area, where you can see that southern part of Europe is highly affected by drought, and that started from the last century, since the 70s, and expanding till now. And we can see also in the eastern part of Mediterranean, there is increase of drought, but also in the altitude of 14 to 18, there is extensive drought intensity, and we can see it also going to south of Africa. So this is the intensity map, and if we see the variability, we have 2 areas where we have high variability. We have all the Mediterranean part, northern part of Africa, and also the southern part of Africa. We have high variability in all over the world. This is the highest areas for variability. And then we calculate the frequency, and in the frequency, sometimes they tell you, okay, we had drought. And someone say, okay, we have it for 4 years. But in reality, if we study it by pixel, we will see that some pixels, you have drought for 7 and 8 and 10 years sometimes. So this is different than when we just generalize the idea that, okay, we have a drought we have drought even for 12 years in certain parts. This is the frequency. And the consecutive, we have in many places here, you can see sometimes the drought is continued, of course, but the majority, we can see 7 and 8 years of continuous drought in many places in the study areas. If we combine the 4 in hierarchical system, we can come to understand where exactly the drought hazard expand. And if we enlarge this, we can see the drought hazard in 7 classes, and over 75% intensity and hazard in some places. We can see the areas. So this is the map which showing us the agriculture drought hazard, and this is the tables for all the countries ranked from 7 to 1, where 7 is the highest drought hazard and 1 is the lowest drought hazard for all the countries which we have studied in this map. Around 80, more than 80 countries. This is one of the examples, Spain. I just selected to tell you that Spain is really suffering from drought. And when I look to Spain, Greece, Portuguese, I understand immediately why they have financial crisis. Stability in agriculture has been reduced since the 70s, even in France. So this is, we have to keep it in mind. This is just I selected for South Africa, just to show where is the areas where there is hazard in South Africa. This is Somalia, and we can see also in Somalia the moderate and high hazard is almost 53%. 50% of the country is under drought hazard. SBI is very interesting to work with SBI. There is many international data for SBI. Spanish already, they have published a lot about SBI. And we can see there is different groups of number of months used for analysis. And for Africa, this is the map of Africa from the beginning of the century, last century, till the beginning of this century, first decade of this century. So this is the SBI. And we can see it in 1 month, in 3 months, in 9 months, in 12 months, in 24, in 48, 36 and 48 also. But you see that the more months we can use the system, it improves the analysis of the SBI appearance for us. This is for Europe, and we can see also comparison between different indexes, Palmer, and also in many during the different years, how it is distributed in Valencia in Spain, and we can compare it with SPI. But if we look to the SPEI, where we can almost see the soil moisture on the ground and how it affects the plant growth, I think this will show us that there is a real drought, because more temperature we have also, plus the reduce in precipitation, with soil moisture is affected very much. And this is, we can see it very clear now in Spain, and we understand why we have the hazard in Spain. We are trying to see who's doing what in that direction, but we are doing also our own analysis now for seasons and months. And for Cairo, we came to this map for the trend in Cairo during the last 15 years. And I think it matches with the data we have seen produced in Spain. The correlation is about 0.8, which I think is very high. Sometimes we have some months it is higher than this. So land cover map is very important now, because we would like to see the exposure here. And if we see the map of land cover of global map, and we take part of Africa, and we see it for different countries, like Spain or South Africa or Somalia, for instance, we can see the distribution of different land use on those countries. But also, because as I told you that we have 263 different transboundary rivers in the world, it is important also to see the exposure of the transboundary rivers. Especially, we have around 59 transboundary rivers basins in Africa only. Now we are talking about green water and blue water. And the more you are on the upstream, it's different than being on the downstream. More in the upstream, you can talk more about green water and the blue water. But the more you are in the downstream, you are talking only about blue water most of the time, because it's limited water. And this is the problem of many countries, and we will see this also in two places, in Nile Basin, and we will see it also in Efrat River. So in Nile Basin, we can see the distribution in the country in general, the Nile Basin as part of these countries. But we can see also that out of the 7,000 million cubic meter falls on the 11 country in Africa, in the countries of the Nile, there is only 1,660 is inside the basin. And Egypt, Sudan, they receive only 84 million out of all this amount. So the rest is in the green water. And part of it only goes to Egypt and Sudan as the blue water. And if you start to build projects over the Nile, that means this small amount, which is less than 1%, is going to be reduced. And that's why the green water, as you can see here in Egypt, is 0. Eritrea 0, Ethiopia 13%, and like this. You can see the distribution. And if we go and see the drought intensity, we can see it is high in the middle of the basin, in Sudan especially. And variability is high up and less down. But the frequency is increasing even around Victoria Lake. And we can see also that it is consecutive in Sudan, especially in the rangeland area and the rainfed agriculture area. And that's what showing us that the drought hazard is very high on most of the places of the Nile Basin. For studying land degradation, we use the trend analysis. And with the trend analysis, we do two different scales. One scale is the regional one, and second scale is the on-site. But just for time, I will try to go faster, because this is the map of land degradation in Africa and Mediterranean. And again, it is ranked in two ways. First way it's ranked as high and moderate areas affected with land degradation. Second is ranked with high, moderate, and slight land degradation. And in reality, if we compare, there is difference between the two. But if you have the drought hazard, it is more linked with the slight, more affected by the slight. The slight land degradation is affected more by drought. This is to show the difference between the two maps according to moderate, high, and this is a map of Spain. This is a map of Somalia, again for South Africa. So drought hazard and land degradation combine together in this map. So we can see where are the areas where we have high hazard of drought and high hazard of land degradation. And we can see exactly Somalia. It is clear in Somalia, it's clear in Eritrea, it's clear in Sudan, and also in many other countries in Eastern and South Europe. This is a map of Spain, and this is the land cover map of Spain, and this is the result of the combination between the drought hazard and land cover. What type of land hazard is more affected? We can see that forest areas and rangelands, and then the mosaic areas between croplands and vegetation are more affected. Land cover for South Africa, we can see also the combination between degradation. And this one I use degradation just to show you that there is degradation, high degradation in the croplands and rangelands, and also in the forest areas. And this is in one of the basins, Efrat River. We can see again land degradation. It is we can see land cover, and we can see the stability of land cover in the Turkey part. This is the upstream of the river, while the rest is very narrow river. And we can compare with vegetation, how effect of hazard on vegetation and the distribution in each of the countries, and how the effect is going in each of the countries. So finally, we need now to see some statistics. And to do these statistics, we have designed or studied several indicators. So economic indicators like the change in GDP, and change in gross national income per person, annual change share agriculture value. And I will show you those indicators has been classified and ranked. And then population also, land use, water availability. This is the data we used from FAO statistics. Agriculture, drought, and economical indicators showing us the relation between hazards and the evaluation of different indicators which has been used, which showing us again that there is a big influence of drought in most of the indicators we used in this study and in different countries. This is just an example to show you the different maps in comparison between the complete 10 years of the study and only 5 years in the beginning of the decade. Just to compare between the 5 years, which we have seen that there is a high hazard between 2005 and 2010, and the 10 years in total. We see that those 5 years is showing us that the hazard has affected most of the indicators highly in comparison with the rest. So I wanted just to share you those data about the different indicators, and I would like to thank you at the end.
Thank you very much, Professor Aryan. Now, may I invite Dr. Harikishan Jayanti to talk about his work on drought issues. Dr. Jayanti went to do his higher studies at Indian Institute of Technology, Roorkee, did his PhD from Utah State University. He has many years of experience working on risk management issues. Quite notably, he's worked for FuseNet for a couple of years, and before that on risk analysis issues with the Risk Management Solutions India for 4 years.
Thank you, sir.
Dr. Jayanti.
Thank you. Good afternoon, everyone. This presentation will be short, and by the end of this presentation, you will realize that you will have on your table a systematic and a scientific procedure to quantify agricultural drought risk. So, first point, the title of the presentation. It's nothing but a probabilistic approach to quantify risk. All I did was give you the results. If I conduct this analysis, what would I get? I would get a loss exceedance probability curve for principal crops cultivated in 3 countries, maize in Malawi, Mozambique, millets in Niger. In this title, in this study, there are 2 other components also. One, this analysis we conducted using satellite estimated rainfall and PET. And second, we used a software platform called GeoWRSI that has been customized for this analysis, for this purpose. Now, quickly, this is where I come from. I worked in Famine Early Warning System Network in US, and its goal is very, very benevolent and very broad scaled. That is, it wants to ensure what is the food insecurity, at what place, and how much of the population is affected in terms of quantity, and in correct time. Is the assessment has to be made in correct time. With this objective, the emphasis is on 3 parts. The availability, where is it available in excess, where is the deficit, and how quickly we can route this, and how efficiently we can do it. In this purpose, we have what is called a very good decision support system which is supporting us, and our own climate services. That means the daily satellite estimates of rainfall and PET are aggregated together into a 10-day average values, and those are used to generate a suite of products that are hosted on the web and freely downloadable. You have rainfall estimates, you have moisture index, soil water index anomalies, you have water requirement satisfaction index, and essentially this is also conducted for rangelands. A host of indexes are there. Now, what this water requirement satisfaction index, most of you know it. It conducts a water balance in the soil root zone for a given crop. It uses precipitation, PET, length of growing period for a given crop coefficients, and the soils, and it conducts a root zone soil water balance, and at end of each decade, from the day of sowings, it churns out to you a number from 0 to 100. If it is 100, the crop is not stressed, its water requirement is fulfilled. If it falls below 50, the crop is really stressed and its yield potential will be totally lost. So you have a scale, you have an index, and this is being done since last 10, 12 years consistently for Africa and Latin America. Now I have a good database of this. That means I have PET values, soil values. So the purpose of the study, the background was the global assessment reports. They highlighted a couple of facts. The recent one highlighted that drought had multi-sectoral impacts, which everyone knows. The primary impact is loss in production, but the secondary impacts, loss in transportation, storages, the tertiary effects, all the manufacturing industries that are based on agricultural produce, they are affected. So it has multi-sectoral impacts, we all know it. What we don't have is a quantitative risk assessment. That means how do we quantify the long-term losses? What are the potential loss for a given area if a drought occurs? So that is what this study is all about. So, title, Characterization of Agricultural Drought Risk Using Satellite Estimated Rainfall. Simple, straightforward. What is the approach? It's a basic template used in any risk analysis. Basically, you have what you call a hazard model, then you have an exposure model. Both these are combined to get your vulnerability. From this, you assess what are the losses, And from these losses, you have loss metrics and a loss exceedance probability curve. It's a simple, straightforward 5-step procedure. Now, in hazard, we can use different hazard indices. You can use standardized precipitation index. You can use SPEI, as he has told, moisture availability index, any index. In this study, we have used water resource satisfaction index, water requirement satisfaction index, because it's the closest crop water index that is reflecting the crop potential under stress and under normal conditions. So I got decadal values since last 12 years. And exposure, I have got district-wise areas in Malawi, Mozambique, Kenya, and Niger, millets in Niger. I've got these areas. All I need to do is build a vulnerability model for a normal year as well as for a drought year. How does it happen? What is the relative picture giving us? Once I have this, okay, the model will look like, what is the relative yield reduction? Can it be explained as a function of relative water deficit? This is in line with the FAO yield reduction factor graph. For all of you who are familiar with the graph, 1 minus actual ET by PET explains the yield, 1 minus actual yield divided by the potential yield. On the same lines, these vulnerability models have been developed in this study. Once I have that, I analyzed the historical data of last 10 years and simulated the rainfall for these areas for 500 years, keeping in mind the statistical and the spatial and temporal characteristics. I generated the simulated data, ran GeoWRSI for these 500 years, and generated the simulated losses. That means I identified the droughts in these simulated data, and corresponding to these droughts, I calculated the losses in yield. Once I have got the simulated losses, drought losses in yield, I multiply it with a reference area to get the loss in production corresponding to different drought events. Simple. So once I get that, I will get a continuous loss exceedance probability curve. If I don't use simulated data, I'll have only 2 or 3 points. So once I get that, I will get all the loss metrics like average annual loss. I'll get losses corresponding to different return period droughts, probable maximum loss, and you have all the loss metrics available. So now we'll get on to the results. All these results have been structured in this way. First few graphs will describe the exposure part, the hazard part. Then next couple of slides, we will discuss about, I'll show the vulnerability model, and the last couple of slides will be the loss curves and the losses. You'll have drought frequency maps. We'll start with Niger. This is the rainfall distribution in Niger. Okay, you see the southern band, you'll have more rainfall. As you go north, you'll have less and less rainfall. That's the rainfall distribution. This is the millet cultivation in the country. You see the northern band cultivates more than the southern band. So what this says is the millets in the northern band are more susceptible to rainfall deficiencies. That's the way world is. And this is the same but production map. But the production is more on the southern belt, more in the southern belt than the northern belt. So you have high yielding areas in the south, less yielding areas in the north, although north is more cultivating more. So you have a real world problem. How do you characterize such an area? This is the vulnerability model which comes out in this area. On the x-axis is 1 minus WRSI. WRSI is nothing but actual evapotranspiration divided by water requirement. That's a ratio. So if I get this, the term 1 minus WRSI is synonymous to what is available in the FAO graph. Corresponding to this water deficit, what would be my yield deficit, relative yield deficit? That means I take a normal year, I take the drought year. So to what degree during a drought year is the yield down with respect to the normal year, nearest normal year? I calculate these differential, these fractions, and I plot one against the other, I get the vulnerability ratio, this vulnerability model. I use this model for historical droughts and simulated drought scenarios to compute the losses for the corresponding years. And how does the product look like? The loss exceedance curve for agricultural drought in Niger, the losses they look like this. Now on the x-axis is the exceedance probability. That means return period can be calculated from them. See 0.1, that means one 10-year drought is associated with such a loss. And in 2000, there was a drought which Niger ended up losing about 450,000 metric tons. So that corresponded to a 1 in 25-year drought. So the drought in 2004 in Niger was a 1 in 25-year drought. So in this manner, that country can have a loss potential map for its own country. So for design purpose, policy making and all. Next, I have the average annual loss map for this country plotted. So each district, each department has a different potential, average annual loss, and this can be used in policy making. Again, these are all loss metrics. Once we go, it's all easy now. Now we have a drought frequency map. That means 1 in 4 years, these districts are affected by drought. And this is the scale. You can easily see what is the drought frequency in this country. So these metrics can be extracted from the risk analysis and the risk analysis. Now, we'll get to maize in Mozambique. This is on the left-hand side, the inset gives you the rainfall distribution from November to March. And on the right-hand side is the area cultivation, maize cultivation in Mozambique. Now, the northern districts, northern provinces are water surplus areas, whereas the southern and central are more prone to drought as we go south. Likewise, this is the production distribution map. So I followed the same procedure, developed the vulnerability model. This is the equation. This is how it looks like. Use that to simulated data, simulated droughts, calculated the loss, determined the loss exceedance probability. This is how it looks like for entire Mozambique. This is for entire Mozambique. Now I have a very interesting graph for you. This is for each province, loss exceedance curves for each province. You see Manica has a different behavior, response to drought, as when compared to Gaza, Maputo, and Inhambane, the blue and the cyan lines. These three provinces have a 0-1 case. That means if you have a drought, the entire district is lost. You have a heavy loss. But Manica, its behavior is different. So if you have, say, a return period of 1 in 4 years, you have more loss coming out of Gaza and Maputo rather than from Manica. And for a severe drought, okay, 0.1, your Manica, the losses in Manica province are huge when compared to these three. So every area has a differential response to drought. These curves help the policymaker, everyone understand how the area is responding, okay, how much area will be affected and to what extent. So we can generate such curves for all other districts. These are the ALs for this country. I just say compare it with rainfall. It's obvious that the northern provinces are seldom affected by drought. The central and the south are more affected, and Manica of all the provinces is affected more because it's the highest cultivated maize cultivation province. And south, it is a water deficit area, so it's obviously drought prone. So drought frequency map, the same results. I plotted it against rainfall so that you can easily compare. Then we come to Malawi. Same rainfall distribution on the left and the maize cultivation on the right side, the insets will show. Sorry for the labeling, the size of the alphabet is small, but still, this band, it cultivates, the southern districts cultivate a lot of maize, but these are drought-prone districts, southern Malawi. So, next, the vulnerability model. It looks like this. This is based on WRSI. And the loss curve, sorry, I'm done. Okay, this is the last graph. And this is the drought frequency map, okay? These are the losses. So conclusion, we have a standard procedure. We know what are the steps, and these are the standard results. If I don't do it, even if you do it, you'll arrive at the same results. So it's a scientific procedure. And the loss metrics can be obtained accordingly. Thank you.
Thank you, Dr. Jayanti. That was a very interesting presentation. Now I invite Julio Serge, a longtime colleague. He is with the ISDR Secretariat, part of the team that's working on the global assessment reports. Prior to this, he was with the UNDP for the Global Risk Identification Program, and before that, he worked many years with LARED. Julio is one of the chief architects of the Descendmentar system, which helps countries develop damage and loss accounting systems that capture losses on a high resolution. He has done some path-breaking work over the last 20 years. I have had the privilege of working with him in half of those 20 years at least. So, Julio.
Thank you very much. Well, I am the lucky presenter that has been left with minus 10 minutes to present. So I should, stop. So thank you very much. I'll try to do this like an Ignite presentation, so in seriously 1 minute. We've heard all the time these huge figures that we have lost, billions of dollars in losses. We believe that's an understatement. It's much more than that. Most of these figures come from a very, very well-known source of disaster data. It's called MDAT. I'm sure all of you know it. Very good data source, as Andrew said, for mortality. They do leave outside a lot of small and medium disasters that we've seen are critical. And they only have like 3 indicators: mortality, economic loss, and affected. We've been looking into several sources. I'm happy Andrew did already most of my presentation here, so I won't have to go into details. Reinsurance data, global data, etc. We've been trying to complement, once we go to countries inside a country, with much, much richer disaster loss data sets. These disaster loss data sets have, first of all, a much richer set of indicators, 16 indicators of losses, like number of hectares of crops lost, number of houses destroyed, number of schools damaged, etc., etc. Physical impact losses, which are much solid than economic loss figures. We have covered small and medium disasters, very important, and we attach this information to small geographic information units. This data is later, provided as, tables, charts, maps, etc. This is, disaster risk reduction 101 thing. I mean, this is the most simple thing that any country can do. You've seen here sophisticated methods for creating loss exceedance curves, etc. This is seriously no rocket science. It's very simple. This is what a disaster loss database looks like. It says number of people killed, damaged, destroyed. It's a very simple thing. It can be done by any government with very simple capacity building process, and it provides extremely important and good results. Like the ones we were seeing on the GAR. You already saw this map on damages on Indonesia and trends. developed countries have been also developing disaster loss data sets. A good example of this is the Sheldus data set. It doesn't have all the richer set of indicators, but it's still, taking into account small disasters, disaggregated information, and so on. And at this point in time, we're still, building this capacity. Our goal is to, at some point, be able to build a global picture from a bottom-up approach, starting from the local level to a global level. Right now, there's very good progress in Latin America and the Americas. We're one country away of being able to do this picture on a continental scale in the Americas. There's good progress in Asia, and there's a lot of things going on in Africa. You know what? I'm going to invite you for Friday session. We're going to spend one full day on this, talking about how to build these data sets, how can they be used, how can you connect these data sets with risk assessments, with studies on environmental degradation, and many, many other topics. So I'm going to stop here. I have like 15 more slides, but I think, we all want coffee, and I'm sure you want to make questions to the rest of the presenters. So thank you very much. Wait for you on Friday, okay? That's the only privilege I have. Thank you.
Thank you very much. We are due for a coffee break now, but before we go, I think we can cut into the coffee break a little bit and take a few questions. So I'll take 2 or 3 questions, if there are any. Gunnar and...
Thank you. My name is Gunnar Paudel. I'm from Nepal. My questions are related to the drought assessment. Of course, as you presented, the analysis kind of straightforward, where if you have satellite images, if you have a good computer, you can produce this. My question now is, when you talk about risk, I think we are really talking about water resources drought. Farmers who have irrigation facilities and they don't get water, there's a false sense of hope, and for a long period they don't get water. I think that is a real risk, where they lose a lot of inputs. I think we need some methodologies to develop and use in many parts of the world. I think for Africa, rainfed agriculture, what you have presented looks very good. The other one is the salinity. Both groundwater, surface water salinity cause a lot of droughts in Bangladesh, Vietnam, many delta. I would like to really see data, approaches, reports on, I will not call hydrological drought, I will call water resources drought. Thank you.
Hi, my name is Dusan Sekulski. I'm university professor here in Bloemfontein, University of the Free State Disaster Risk, former scientific advisor for United Nations University in Bonn, Germany. Thanks for all this presentation. Little bit comment and maybe concern. In your model, you're talking about risk and you have a hazard, exposure, vulnerability. Talking about drought, I would rather focus on dry spells or wet spells, if you talk about wet spells, than drought, because without proper resilience or without proper manageability, not every dry spell will make a drought, and very often drought happen without dry spell. Maybe it's just terminology issue, but again, think about manageability and then put in your risk model, and then maybe you can talk about drought. Thanks.
Okay, one last question, and then you can respond.
Thanks. I have 2, but they're very quick. So first, a question on the agricultural drought risk, in Malawi and elsewhere. You probably didn't, look at correlation of rainfall and crop yields, but I'm just wondering if you also, in your analysis, taken onto other account, like kind of cross-check that against factors like the wealth of the farmers and the types of seeds they're using, and because we've seen in some other countries, like in Senegal, that primary drivers of loss were actually other factors other than rainfall. So how you kind of cross-check those data. And then I was wondering on the damage and loss assessment, whether there's a move to look into spending on disasters. So we know, we have standardized methodology for accounting for damages, but then trying to account for, spending I just had to try to do this recently, and it was very difficult. Government spending on disasters, private sector spending, and individualistic, if there's any sort of advances there. Thank you.
Let me answer your first question.
Thank you.
Let me answer your first question. It's not based on rainfall deficiency. It's based on water requirement satisfaction index. What it does is it conducts a soil water balance in the root zone, crop root zone. So it takes into account the type of crop, it uses the crop coefficients, everything, precipitation, PET, soils, and then calculates what is the deficiency of water in the root zone that is available for the crop to survive. So it is not per se rainfall. So it is closer to the crop water needs. And that is what the theory says is more the deficit, more the effect on the crop yield. So that's where we are shifting from rainfall deficiencies and indices to more related to, by using crop indices, we are more closer to representing what is an agricultural drought. Now, another thing, most people confuse when we use the meteorological indices, okay, and meteorological droughts. Not all meteorological droughts result in agricultural loss in production or reduction in crop area. So WRSI is closer to that scenario. So when we talk about drought risk assessment, we are talking about agricultural drought risk assessment. So there is a distinct line. We have taken the fork. Okay, we are going more towards the ag part. That means crop response to water deficit. As regards to government spending, those are the guys.
Let me respond to the question of government spending. Loss data sets can be very flexible. We use an open source system that allows these databases to be expanded to multiple variables. In general, we've seen the tendency on A to also record, along with direct losses, some sort of indirect losses, and a lot of data on relief and response and disaster attention expenses. We have been developing over the past 2 or 3 years mechanisms to take these direct losses and extrapolate on other types of losses, using, for example, loosely the ECLAC methodology for disaster loss, for damage and loss assessment on post-disaster situations. But it's still, as in many things, unresolved subject. We believe that governments do not know, in general, what they lose. We've asked even, European governments. You see the blue map, the blue areas there. They don't know. Germany, France, they don't have a full figure of what are their losses, not even the direct ones. So the idea is we have to start, recording our losses. If we don't know what we lose, how can we really work and monitor our progress? That's the fundamental message.
Have you seen River Dye? This is very important to recognize that people depend on irrigated agriculture, and suddenly the river which is used to use is dying. If you see an area where you have rangeland and this area received less than 200 millimeter and the people depend on their living on this rangeland and they don't receive any more, they are in cycles of drought and they don't have any more rangeland. It is already a rangeland for 2-3 years each decade. They immediately leave the area, and this has happened in most of the Arab countries in desertic areas where they have a rangeland covering less than 15% as total coverage. If you go to the forests in Panama and you look to the forests where you receive used to receive 1,200 millimeter, and now we are receiving around 1,000 to 900 millimeter, and you start to see the life type inside the forest. It's changed. The type of trees is changing, the kind changing. It's economically will change because the birds and the animals and many of the biodiversity inside the forest is also has been left or changed. So the drought is making a big difference in many places if it is there for long time. And we have seen the cycles of drought in many places. It is now coming very close to each other. I will give you example of Syria, where 1.3 million has left their origin villages and places, and they left to cities just in the year 2007, 2008, after a cycle of drought started in 2005 and ended in 2009. But they couldn't stand, their loans has accumulated, and they have to split the families sometimes. And first time you see conservative women working in a coastal area in greenhouses. It's a lot of social and economical stories you can tell if you are talking about drought impact on socio and the economy. And of course, if we deal with all those issues, we keep in mind that uncertainty in rain-fed agriculture between the zone which is receiving rainfall of about 150 to 400, and you have evapotranspiration, high evapotranspiration. This is areas where you have uncertainty of agriculture. And with this uncertainty of agriculture, the people are now trying to find alternative opportunities. So if you look to the world in globe, and you look to the rangeland in general, and you look also to the areas where we used to produce maize, wheat, and barley, you will find that those are the areas, according to the IPCC report, is going to be affected more by drought. This will affect the food stability on the globe, which we already felt it after each cycle of drought, and this will, according to all the scenarios we have seen, and according to IPCC SRAX report, this is going to be expanded in the 21st century, and we will feel it, all of us, not far from now. So we are really under threat of drought, and this is an issue which we don't feel it sometimes because it goes very slow as a disaster, but it as accumulated, we immediately get the feeling of this disaster, how it has really affected our stability, not in one point, but the stability in the balance in the globe, on food production, in migration, in water scarcity, and also biodiversity and land degradation.
Thank you very much for very rich presentations, interesting questions. I'm sorry we have run out of time, 15 minutes into the coffee break, right after which there is a session on floods, I think in the same room. So thank you very much, and thank you for being here.